Hello and welcome to another video for Calculus 1. We are in a series of videos with application of derivatives. So the other application that we are going to discuss today is the optimization problems. So in calculus, maximizing and minimizing a function is very important. It has a wide variety of applications. So that's what we are going to discuss here, which is called optimization. So here we try to optimize in some cases we try to maximize something, and then in some other cases we might want to minimize something. So that's what we are going to look at. So in order to solve a optimization problem, first we look at the problem, and then so we have to create our own function. So for that we introduce variables depending on what we want to find. Okay, and then if necessary we might have to draw a figure and then label the variables that might help us to write the function. So the most important part is writing the objective function. So this is the function that we are going to maximize or minimize, and then write it in terms of the variables of the problem. Okay, so write any equation. So other than the objective function we might have other several equations, so we have to write those equations relating the independent variables. And then this is very important. So we are going to use this equation to write the objective function as a function of one variable. That's what we need to do. Otherwise, it would be challenging to find. I mean, we cannot find the maximum or minimum if we cannot write, if we don't write the function as a function of a one variable. Okay, so this step 3 is very important. Then after that, we have to identify the interval of interest, because when we see a function, any function, random function would have a different domain. So we need to figure out what is the domain that we are interested in maximizing the function, because it has to make sense with the context. And then we'll use the method of calculus. That is, we'll use first derivative to find the critical numbers, and then maximum and minimum. Then we might have to use the second derivative in order to confirm there is a maximum or minimum. Also, we might have to use the endpoints depending on the problem. Sometimes it just becomes obvious, so we don't have to do that, but sometimes we might have to do that. So let's get started with an example. So this is an example where it says a rectangular area is to be enclosed by a fence and divided into two equal parts, with a fence running along the division parallel to one of the sides. If the total area is 216 square meters, find the dimensions that will minimize the total length of the fence. So how much fencing is required? So let's go ahead and draw first. So we have a rectangular area that we are going to um, enclose. So let's go ahead and draw that. So let's say this is the rectangular area, and then it is divided into two parts. So I'm going to divide that into two parts. So let's say this length from here to here is y. Okay, and then let's say this length here is x. So if that is x, and this is also x, this is also x, and this is also y. So now let's see what is given. We are given the area of the area of that rectangle. Okay, so area is given by, so area A is given by length times width. So the length is y, width is x, so it's x times y. Okay, and then we are given the area, so this implies x times y equals 216, and then if we solve for y we get 216 over x. Now the next thing is our objective function. So what are we trying to maximize or minimize here, or optimize? So we are trying to minimize the total length of the fence. So let's say the length of the fence is denoted by L equals, so if you look over here, the length of the fence is this length y the upper length here y, so which means 2y, and then this length x, this length x, and this length, the one that is dividing the rectangle into two parts. So we have the total length as 3x plus 2y. And this is the function that we are trying to minimize. Okay, so this is the objective function here. Now, as we know, we want to write these in terms of one variable. So that's why I already solved for y here. So I'm going to replace y with this one. So let's say L as a function of x equals 3x plus 2 times 216 over x is, so we can write 2 times 216 over x, which is L of x equals 3x plus 432 over x. So this is the objective function, or this is the function that we are trying to minimize, okay? Now, we have to find the critical numbers. So let's go ahead and find the first derivative. So L prime of x equals 3. So now the derivative of 432 over x, we know that derivative of 1 over x is negative 1 over x squared. And then we have that 432. So it's just minus 432 over x squared. Now in order to find the critical number, we are going to set the first derivative equals to 0, or 3 minus 432 over x squared equals 0. Now that becomes 3 equals 432 over x squared. So let's take this over here. Now if we do the cross multiplication, so we get 3x squared equals 432 divided by 3. So we get x squared equals 144. And then when you take the square root, we get x equals 12. So we are not going to take a negative number here because we are talking about the length. So length cannot be negative. So we got x equals 12. So when x is 12, that's going to give us the minimum length of the fence, okay? But just to make sure that this is true, or this is going to give us minimum, what we can do is we can, since we don't have any other critical number, so that must be the number that gives us minimum. But just to make sure that it is the right number, we don't have other numbers. So just to make sure that what we do is we'll find the second derivative, and then we'll do the second derivative test. So from here, if we find the second derivative of that function, so derivative of 3 is 0, then we have negative 432 over x squared. Again, the derivative of 1 over x squared is negative 2 over x cubed. And we have this negative 432 over here. So the second derivative becomes 864 over x cubed. And it is positive, okay? So we'll get a negative here. We already have a negative. That makes it positive. Now, if we find the second derivative, the value of the second derivative at x equals 12, so 864 over 12 cubed, obviously this is going to be positive. Now, the second derivative positive implies we have minimum, okay, so minimum at x equals 12. So with that, we know that we are going to get minimum when x, this x is 12, then let's go ahead and find y, because we are trying to find the dimension of that rectangle. So y equals, so we'll just use this equation here, okay, so 216 divided by 12, which gives us y equals, so 216 over 12 is 18. So that means the dimension of that rectangle is 12 is in meters, so 12 meters by 18 meters. Okay, so this is the dimension. Now we are also asked to find the length of the fence, how much fencing is required. So length of the fence is given by this equation right here. So L equals 3 times x means 12 plus 2 times y means 18, and that gives us L equals, so if we multiply that, we get 72, and it is in meters. So the length of the fence required to enclose that rectangle is 72 meters, and the dimension of the rectangle is 12 meters by 18 meters. Let's look at another example. So an open top box is to be made from a 24-inch by 36-inch piece of cardboard. So what we are doing here, so this is the dimension, okay? So we have a cardboard. So let's draw that. So what we have is we have 36-inch by 24-inch. Now what we are doing here is we are going to make a box by cutting cutting a square, removing a square from each corner. So we are going to cut each corner. So we are going to remove this corner by cutting that small square. So when we do that, this is how it's going to look like. Okay, so we are going to cut that. So it's going to look like this. Okay, so we don't know how much we are going to cut. So that's what size square are we going to cut so that the volume is maximum. Okay, so let's say we are going to cut X. So if we cut X on each side, so X, 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 and X. So the length that we are going to cut is X, or we are going to cut X by X square. So now what happens here is if we cut X inches on each side, so we cut X on this side and we cut X on this side, so the total length was 36. Now this length becomes 36 minus 2X. And this length becomes 24 minus 2X because we are cutting X from each side, each edge, okay? Now when we fold this, so if we fold that, then that's going to create a box and with an open top. So there is no lid on the top, okay? So now this is the dimension of that box. So the length of the box is going to be 36 minus 2X. The width of the box is going to be 24 minus 2X. And when we fold this, so this is going to be the height. Okay, so when we fold that, so the height is going to be X inches. Now, the volume, that's what we are looking for. So our objective function here is the volume. So volume of that box, let's say it is the function v of x equals the length, which is 36 minus 2x, times the width, which is 24 minus 2x, times the height, which is x. And then if we multiply this, so this is what we are going to get. So this gives us, let me write it here. So v of x equals, so when we do the multiplication, 864x minus 72x squared minus 48x squared plus 4x cubed. So when we multiply here, okay, and then by x, so that's what we get, and then we multiply here, so you can do the multiplication. So if we combine the like terms, so we are going to get v of x equals, so let's write this in order, so 4x cubed minus 120x squared plus 864x. So this is the function, the objective function that we are trying to maximize. So now, in order to find the maximum volume, we need to find the first derivative and then find the critical numbers and then find the x value, which gives us the maximum volume. Okay, so let's go ahead and find the first derivative. So v prime of x equals, so 12x squared minus 240x plus 864. Now when we do v prime of x equals 0, we get 12x squared minus 240x plus 864 equals 0. And then if we divide everything by 12, we get x squared minus 20x plus 72 equals 0. I don't think we can factor this in, so we are going to use the quadratic formula to find the value of x. So x equals, so negative b, so we have negative 20, so negative of negative 20 is 20 plus minus square root of b squared means 20, negative 20 squared, which is 400 minus 4ac over 2 times 1. Okay, so now this gives us x equals, so we have 20 plus minus, so inside the square root, if you simplify that, you get 112 divided by 2. So from here, we can say, okay, so 20 plus or minus, so if we break that 112, so that is 16 times 7. So square root of 16 is 4, so we can rewrite this as 20 plus or minus, so 4 square root of 7 over 2. So when we simplify that, we get 10 plus or minus 2 square root of 7. So basically we have x equals, so we have two different values, okay? So x equals 10 plus 2 square root of 7. And if we put that into the calculator, we are going to get 15.29, and it is in inches. And then the other value of x is 10 minus 2 square root of 7, and that's going to give us 4.71 inches. Now these are the two possible values, okay? So if you look at, so we have both positive number, and we might think, oh, these both are possible, so which one is the correct one? But if you look carefully here, this is what's happening here, okay? So if you look at the first one, so we got 15.29 inches. So is it possible to cut that from each side? So the total width of the cardboard is 24 inches, but if we try to cut 15.29 from each side, it's not possible because we need more than 30 inches. So it's not possible to cut 15.29 from each side, which basically means this is not possible. So that means the only possibility that we have is 4.71. So that's going to give us the maximum volume. Now, in order to make sure that it's the right one, you can always find the second derivative and then do the second derivative test where you should get a negative number, which implies that we have a maximum. So I'm not going to do that, but you can always try to do that just to make sure that you had the correct number, okay? So we are just asked to find the length of that square, so we are not going to find the maximum volume. But if you were asked to find the maximum volume here, so what you would do is you would take this number 4.71 and put it into the original function right here. So if you take that number, plug it in here, that gives us the maximum volume. So maybe in the homework or in the test, you might be asked to find the maximum volume. So you need to do that, okay? But here we are just asked to find the size of the square. So we are going to cut 4.71 inch by 4.71 inch square from each corner in order to make that box. Let's look at another example. This is one of my favorites. So this is a rectangle is constructed with its base on the diameter of a semicircle. So let's go ahead and draw the semicircle. So let's say this is the semicircle. Now what this is saying is rectangle is constructed with its base on the diameter of the semicircle. So you're going to make a rectangle here with the one of the bases on the on the diameter of the semicircle. Okay, let's say this is the center of the circle. So now the radius of the circle is 5 centimeters. So this is 5 centimeters, or we can say this. So here, this is the radius of the circle. So this is 5 centimeters. Okay. And the two vertices on the semicircle, what are the dimensions of the rectangular with the maximum area? So let's say this, okay? So let's say the length from the center to this part is x, and this length is x, and let's say this length, the height of the rectangle is y. So now our goal is to find the maximum area. So before that, let's go ahead and write the relationship between x and y, okay? So if we just look at the right triangle here, if we just look at this right triangle, what we see there is x squared plus y squared equals 5 squared. So we have x squared plus y squared equals 5 squared, which is 25. Now we can solve for one of the variables. So let's go ahead and solve for y. So we get y equals square root of 25 minus x squared. So let's leave that there. And then let's find the area of the rectangle. So area of the rectangle, so area A equals, so the base of the rectangle is x plus x, 2x, or the length. Okay, so it is 2x times width, or the height of the rectangle is y. So the area is 2x times y, where we have y equals 25, square root of 25 minus x squared. So we can rewrite this as a function of x. So area as the function of x equals 2x times y is just 25 minus x squared. Okay. Now in order to find the maximum area, we need to find the first derivative, find the critical numbers, and then find the dimension, which gives us the maximum area. So let's go ahead and find the first derivative. Here we have to use the product rule. So first function, which is 2x, times the derivative of second function. So the derivative of this function is 1 half 25 minus x squared to the negative 1 half times, so we have to find the derivative of inside function, which is negative 2x, and then plus second, then the, so we have first function derivative of second, now second function, which is square root of 25 minus x squared times the derivative of first function, which is just 2. Okay, now let's go ahead and simplify this a little bit, clean this up. So a prime of x equals, so these two cancels out, and then what we have is we have x times negative 2x, which is negative 2x squared. And then this has a negative exponent, so we can put it in the denominator and then change that 1 half into a square root. So we have 25 minus x squared plus 2 square root of 25 minus x squared. I think that's all we can simplify this to, okay? Now the next step is we are going to set the derivative equals to 0 and find the critical numbers. So for that, what we are going to do is, so we take this derivative, so the whole thing, and set it equals to 0. So negative 2x squared over square root of 25 minus x squared plus 2 times square root of 25 minus x squared equals 0. So what I'm going to do here is I'll just take, this is already negative, so I'll just take that on the right hand side, and then my equation is going to become this. Okay, so 2 times square root of 25 minus x squared equals 2x squared over square root of 25 minus x squared. And then if we do the cross multiplication here, so this is over 1, and if we do the cross multiplication, then we are going to get, so 2 times, so square root of 25 minus x squared times the square root of 25 minus x squared is just 25 minus x squared equals, we will get 2x squared on the other side. So let's take this one up here, and then so let's solve that. So 2 times 25 is 50 minus 2x squared equals 2x squared. So if we put 2x squared on the same side, we get 4x squared equals 50, and that gives us x squared equals 25 over 2 if we divide by 4 on both sides. Or that is going to give us x equals So square root of 25 over 2 is just 5 over square root of 2. So when you take the square root of 25, it's 5, and the square root of 2 is 2. Again, we're just going to take a positive number here because we are talking about the length, so don't worry about the negative number here. So this is what's going to give us the maximum area here. So we will take this one and then we'll find the height of the rectangle. Again, if you just want to confirm that this gives the maximum area, you have to find the second derivative. It is a little bit challenging, okay, and then verify. But it totally makes sense. If we have x equals 0, then we really cannot make a rectangle. So that's the maximum. I mean, x equals 0 is the minimum value, or the is that 0 is the minimum value of x, and the maximum value of x can be 5, which is, again, we don't make a square, I mean the rectangle. So if x is 5, it's just 5 this side, 5 this side, which means it's just a line, it's not a rectangle. If x is 0, then it's just a dot, so it's not a rectangle. So these are the endpoints. So x is between 0 and 5. Another way to say this is the domain of interest. So at 0 and 5, we really cannot make a rectangle, so there is no maximum. So that must be the maximum because we just have one critical number, okay? That's how we can make sure that it is the only value that gives us the maximum. Otherwise, if you are not sure, you can find the second derivative and do the second derivative test. But I'm not going to do that here. So now let's go ahead and find the height of the rectangle, which is y equals, so we can just put it right here in this equation, okay? So y equals square root of 25 minus x squared. So x squared is 25 over 2. So if you simplify this, so you get 50 minus 25, which is 25 over 2, and then square root. So that gives us y equals 5 over square root of 2. That means we will have instead of rectangle, we'll have a square of dimension 5 over square root of 2 times 5 over square root of 2. So the dimension of that rectangle is 5 over square root of 2 by 5 over square root of 2. Okay, so that is the dimension of the rectangle, and the units is centimeters. So centimeter, centimeter. So in general, let me tell you something. In general, I think this is what happens here. So the dimension would be x equals r over square root of 2, and y equals r over square root of 2. So it is the radius divided by square root of 2. So if I change the radius, we can just use this formula right here. X equals r over square root of 2. That is going to give the um, maximum area of the rectangle, okay, if we change the radius, because the problem is going to be same, all the steps are going to be same. The only thing that's going to change is the radius, this 25. So in general, we can just let that 5 be r, and then we can work on this problem. We should get x equals r over square root of 2. Let's look at another problem, which is very similar to that semicircle, but now instead of just saying semicircle, what we have is we are given a function here. So let's go ahead and grab that function. You know that the x-intercept for this function is square root of 8 and negative square root of 8. So let's say this is negative square root of 8. This is positive square root of 8. And the y-intercept is 8. So basically, the graph is going to look like this. That is this parabola. Now it's very similar to the previous example because what we are going to do is we are going to make a rectangle like this. Okay, so my diagram is not uniform. Don't get confused. I didn't draw this very well, but this is symmetric. So this is going to be x and this is going to be x. Okay, and then we have this. We really don't need the radius here. So what we have here is the height, which is y. Okay, so let's go ahead and find the area. So area is given by the base, which is x plus, is same as the previous one, which is 2x times the height, which is y. Okay. Now, area as a function of x equals 2x times the height of the rectangle is actually the y, which is the y value of the function, and it is given y equals 8 minus x squared. So 8 minus x squared. That's why we don't need that hypotenuse here in that right triangle. We don't have to use that because we are given the function here, okay? So this gives us a of x equals 16x minus 2x cubed, okay? Or if we find the first derivative, so we are going to get 16 minus 6x squared. Now for the maximum area, we are going to set the derivative equals to 0, which implies 16 minus 6x squared equals 0, or 6x squared equals 16. Or if we divide by 6, then we get x squared equals 16 over 6, or x equals 4 over square root of 6. So that is the x value. Again, it's very similar to the previous problem. So if we make x 0, we have a dot. If we make x equals the x-intercept, then we just have a line. So we really cannot make a rectangle. So this is the only possible point that gives us the maximum area. Again, if you want to check, you can just find it's not that hard here. So you can find the second derivative. So if you find the second derivative, it is negative 12x, and if we plug that in here, we get a negative number. Negative second, if the second derivative is negative, that means we have the maximum. Okay, so the maximum area is given by the rectangle with x value is 4 over 16, or the length of the rectangle at the base, whatever you call, is x plus x 2x. So 2 times 4 over square root of 6, which is 8 over square root of 6. And the height or the width of the rectangle is y value, which is, so we can put it in here. So y is 8 minus x squared, which is 16 over 6. And then if we simplify this, we're going to get 16 over 3. Okay, so this is the height, that many units, and this is the length, that many units. If you want, you can change it to decimal. I'll just leave it as exact. So that is the dimension of the rectangle. Let's look at one more problem. So this is a try now problem. So if you want to pause the video and try this example and then resume your video and then see the work, that's totally fine. So this is an interesting question again. So we have a piece of wire which is 20-meter long. Okay, so what we are basically going to do here is we are going to cut this into two pieces, not equal pieces. It might be equal, but it doesn't say that. So any two pieces, and we'll take one of the pieces and we'll bend that into a square. Okay, so we'll take one of the pieces and we'll bend that into a square, and we take the other piece, the remaining piece, and we'll make a circle. So we are making two different shapes. How should the wire be cut so that the total area enclosed is maximum, and how it should be cut so the area is minimum? So we are going to find both max and min for this function. Okay, so let's start with this one. So we know that total length of the wire is 20 meters. So let's say that we have a circle and the square. So let's say we have a circle here, and then we have a square. So let's say the length of the portion that is cut and made a circle is x. So x is the length of the wire that is used to make a circle. Okay, so let me write L for the circle is x, and then we know the length for the square is 20 minus x. So for example, if you cut 5 meters for circle, then 20 minus 5, 15 meters is used to make this square. Okay, that's what it means. Now we need to find the area for both. So to find the area of the circle, we need the radius. To find the area of the square, we need the side, okay, length of the side. Now, when you cut that wire and then when you bend it to make a circle, that means this length of the wire gives the circumference of the circle. So we know that the circumference of the circle is 2 pi r. So 2 pi r is the circumference equals the length of the wire. So from here we can find the radius of the circle that we made is x over 2 pi. Similarly, this is the perimeter of the square. So we have a wire and we bend it and we made a square. So that means this length of the wire is the perimeter of the square. So the perimeter of the square is given by 4 times the length of this square or the side of this square. Or if you divide the perimeter by 4, then we get the side. So this is the perimeter. So the side of this square is given by 20 minus x over 4. Now the area of the circle is pi radius squared. So pi radius is x over 2 pi squared. And when we do that, we get pi over, we have a pi squared in the bottom. So in the numerator, we just have x squared over 4 pi. So don't get confused here. We have a pi squared. This pi cancels out one of the pi. So we just have 4 pi in the denominator. Similarly, the area of the square is given by the side square, which means 20 minus x over 4 squared. So which is 20 squared is 400. So if you do 20 minus x times 20 minus x, so this is what you are going to get. So 400 minus 40x plus x squared divided by 4, or we can write that as a equals 400 over 4 is, sorry, this should be 16. What did I do? So when we square 4, we get 16. This should be 16. So 400 over 16 is 25. Minus 40 over 16 is 5 over 2x. Then we have 1/16 x squared. Now we are trying to find the maximum and minimum for the total area. Okay, so maximize and minimize the total area. So the total area a as a function of, let's say, x is given by area of this circle plus area of the square. So let's write the area of this square, which is 25 minus 5 over 2x plus 1 over 16x squared. So that's the area of the square, then plus the area of the circle, which is x squared over 4 pi. Now it's the same process. So we are going to find the first derivative to find the critical numbers. So a prime of x equals derivative of 25 is 0. So we have negative 5 over 2 plus, so when you find the derivative, this is 1/8 x plus 1 over 2 pi x. Okay. Now set the area equals to 0. So if we, set the first derivative equals to 0. So which is negative 5 over 2 plus, so actually we can factor out x from here. So we have 1/8 plus 1 over 2 pi equals 0. Or if we take the negative 5 over 2 on the other side, and if we combine these two, okay, so if we combine that fraction, this is what we are going to get. So we have x times 4 plus pi over 8 pi. So you can add those two fractions and simplify, equals 5 over 2. So let me go ahead and write it here. Sorry. So let's write that here. Okay. So that implies x equals 5 over 2 divided by this means times 8 pi over 4 plus pi. Okay. And then x equals, so if we simplify that, we are going to get 20 pi over pi plus 4. Or if you put it into the calculator, this is approximately 8.8. Now, a couple of things here. We need to take the endpoints, which means we have a wire of 20 meters. So if we don't cut it into any pieces, or if we take the whole thing. So for example, if our x can be, so if we look at the domain for this function here, okay, so if we look at this function right here, the area function, the domain of interest is, or the x value is in between 0 and 20. So x is in between 0 and 20. So now this is what it means, okay? If we take x equals 0 means we didn't make a circle. We took the whole, so x 0 means there's no circle. So we take whole thing, the whole 20-meter long wire, and we made a square. Or if we say x equals 20, that means we took the whole thing and we made a circle and we didn't make a square. But if we take anything in between 0 and 20, that means we cut that into two pieces and we made a square and a circle. So now this one x equals 8.8 means the piece that we took to make a circle is 8.8, and the remaining one is the piece that we took to make the square. Okay, but we have to check what gives us maximum and minimum area, so we still have to check those endpoints. So what we are going to do now is, so our endpoints are 0 and 20, so we are going to find evaluate the function a at 0. So if we plug in 0 here into this function, what we are going to get is we are going to get 25, because this is 0, this is 0, and this is 0. Also, we are going to take the other endpoint, 20. So plug 20 into this function right here. You can put it into the calculator. I have calculated the value, which is 31.83. And then if we plug in this number, critical number that we obtain here into our original area function here, we are going to get 14 as the value. Okay, so now this is what this suggests. Okay, so we have a maximum right here, and then we have a minimum right here. So as per the question, we'll get a maximum if we take the whole wire and make a, so x equals 20 means if we take the whole wire and make a circle. So x equals 20, or just make a circle, no square. Okay, in that case, we are going to get the maximum area. The other one will get the minimum area if we take x equals 8.8, and that is for the circle. Okay, and then for the square it is 20 minus 8.8, which is 11.2. So if we take 11.2 and make a square, and then take 8.8 and make a circle, that gives us the minimum area. So that's what this means. Okay, so let's just stop here for this video. I'll see you again in the next video.